Hey guys, Mr. Betts here. I want to talk to you about some application problems that we're going to use derivatives for. And so we're going to talk about something called differential equations, and then we're going to look at some models, so mathematical models that we can create with differential equations. So let's start with a fairly simple definition. We're going to talk about this thing called a differential equation a lot. And a differential equation is a pretty simple idea. It's just an equation that has a derivative in it. So we're going to use these differential equations to model situations that involve rates. So remember, a derivative represents a rate of change. So we're going to look at problems where some quantity is changing, usually with respect to or proportional to some other quantity. A lot of times they're going to be motion problems, but there's a huge variety of problems that we're going to look at using differential equations. There's two types of proportionality or variation that we're going to look at. The first is direct variation or a direct proportion. And the idea with a direct proportion is that as one quantity increases, another quantity increases as a result, and it's a rate that's a constant multiple of the first. So some examples would be like how much money you get paid for working a job. So if you get paid hourly, your wages are going to be whatever your hourly rate is times the amount of time that you work or the number of hours that you work. So the wages that you get and the time that you spend are a direct proportion. As you spend more time working, you get paid more for working. Buying gas is the same way. So the amount that the gas costs is directly proportional to the amount of gas that you buy. So you go to the gas station, they have an advertised price. That's a price per gallon. So the more gallons you buy, the more you pay. And it's directly proportional because for every gallon that you increase, you pay the exact same amount in addition. Um, Jogging, this is a little bit less exact, but let's say that you're able to jog a constant speed, then the distance that you jog is directly proportional to the amount of time that you jog, because as you jog for the same speed for a longer period of time, you're going to jog a longer distance. This is only a direct proportion or direct variation if your speed is constant. You will see lots of problems in math where we know things aren't necessarily going to be constant, but we make assumptions about them, and sometimes we pretend like they might be. The other type of variation that we're going to talk about is called indirect variation or an inverse proportion. So two quantities are inversely proportional if as one goes up, the other one goes down, and they have that relationship in a very specific manner so that when you multiply the two quantities together, you always get the same number. So let's say you're working on a project that is going to take 10 hours to complete. The more people you have working on that project, the less overall time it's going to take. So group work would be an example of an inverse proportion. So the more people you have working on it, the less time it's going to take to complete the project. If we use the jogging example again, and again, assuming you're jogging at a constant speed, if you're going to jog, say, for a mile, the faster you go, the less time it's going to take. So for a mile, if you jog, say, 10 miles per hour, it's going to take you 6 minutes. If you jog 6 miles per hour, it's going to take you 10 minutes. So that product is always going to be 60 regardless of how fast or slow you go. Gravity is another example. So this is an inverse proportion. Those of you that have taken physics before, you might be a little familiar with this. Newton's first law of motion, I believe. And it basically says that the force of gravity is inversely proportional to the distance between the two objects, and actually more specifically, the square of the distance between the two objects. So an inverse proportion doesn't have to be, speed times time equals distance, where distance is constant. So this is a constant. But in this case, the force of gravity times the square of the distance between them is going to be some constant. So I should probably use G for the force of gravity. But that's another inverse relationship. Now, with both direct variation and indirect variation, we're going to be looking at rates of change. So these are very simple pre-calculus type problems, but we're going to be looking at the rate that, say, a volume is changing is proportional to the volume itself. So the bigger the volume is, the more the volume is increasing. Or more likely, the change in the principal value of an investment is directly proportional to the size of the investment. So the more money we have invested, the more interest that we can earn on that. And the same thing is going to be true for these inverse proportions. We will see problems where a rate of change is inversely proportional to some other quantity. So we might see the rate of change of our speed, which is an acceleration, or let's say the rate of change of our position with respect to time is inversely proportional to where we are. Okay, I don't know of an example where that might actually be the case, but it could be. So in inverse proportion, we're going to see a constant divided by a quantity, where a direct proportion, we're going to see a constant multiplied by a quantity. As I mentioned before, there are going to be lots of different types of problems that we're going to see with this. So I would encourage you to look at the example problems and do a little bit of practice with some example problems to check out that variety.